that every mathematician will do their own views. Battle of Trafalgar, NelsonToNewton. And the crazy who first came
So thank you. So I teach at a small liberal arts college where frequently I have students who, while most of them are mathematicians, I do occasionally get people from other departments and people who are not math majors and are just interested. And it's always a challenge. What examples do you want to use? What do you want to go to? You know, I am a baseball fan. I love going to baseball and sabermetrics whenever possible, but it's what can I do that will bring in people from a diverse background? And one of the things I love about this topic is it's a chance to bring in a lot of results from history. Of course, this is also scary as you find out how much history people do not know, but that is a separate talk. I would also like to thank the organizers for putting me directly after the previous talk, which has done a lot of the background and the mathematical modeling, which will allow me to focus a little bit more on implementations of this in the classroom. Okay, so the goals is I want to discuss opportunities to introduce mathematical modeling as early as possible. So my department has had conversations for, I guess I'm old enough that I can say decades now, about what do we want to require a mathematician to know in the 21st century. You know, do we want them to know programming? Do we want them to know mathematical modeling? And where can we put these in the curriculum? And so I want to try to get this as early as possible. There is a great book that just came out, 6 Pillars of Business Calculus or something like that, where they use the SIR model not to discuss the progress of a disease in a society, but the market penetration of a new product, and just trying to find what can you do that will connect with your audience. And so I want to try to start off with a simple system of differential equations, a simple real world problem to model, and then discuss how we can go with that. So I'll try to motivate the mathematics that the students are going to be seeing, and finally highlight the importance of the fact that this is the 21st century. You're not going to be solving these differential equations by hand. There are a lot of packages out there. I was a double major with physics, so I was trained on Mathematica, but there's other software that you can use. Okay, so I haven't taught Calculus 1 officially for 15 years, but I have used this in Calculus 2, in Calculus 3, in probability, and operations research. Whenever possible, this is one of my favorite go-to problems because it has tremendous real-world applications, and at least some of my students are familiar with the Battle of Trafalgar. Okay. The other thing is people are usually familiar with discrete versions of this, the predator-prey problem. So it's something that we can build upon. All right. So the prerequisites, very minimal for something like this. I want people to be aware of the exponential function and its derivatives, so that when we talk about the solutions, they have some understanding of what these are. As I mentioned before, the predator-prey problem, where they have a lot of intuition. This is something that is physically reasonable to them, and they can see some very interesting cycles, as was just mentioned in the previous talk. I do not assume any historical knowledge. Usually there's 1 or 2 students in the class who have some familiarity with the Battle of Trafalgar and the Napoleonic Wars. Okay, out of curiosity, how many people are familiar with the Battle of Trafalgar? Okay, so I'm not going to go into too much detail, but it was one of the most decisive battles, I think, in the history of the world. We will see at the end of the talk just some of the statistics about just what the results were in terms of the British naval forces versus the combined Franco-Spanish Armada. And it completely turned the tide of the Napoleonic Wars. So this is a battle that had real historical significance. You had 2 major fleets getting ready for an engagement. And of course, you have the interesting question, what should your strategy be if you're the commander of each force? And so the British fleet was actually outnumbered by the French and Spanish Armada. Now, you can ask as to whether or not the ships of the 2 powers are equal. Maybe one set has better sailors, better commanders, and so their ships might be better made, better manned. That might give them a little bit of an advantage. So there's a lot of interesting complications you can do to the model, but of course, keep it simple, stupid. Let's start off with a nice, easy model, see what we can gain from that, and then try to figure out what strategy should you take. And so I'll open this up to a discussion to the students. If you were the commander, what would you want to do? How would you want to try to distribute your forces against the enemy forces? And sometimes, I've done this many times, the students come up with the idea of trying to split the enemy forces into two. So maybe you have most of your forces attacking a good amount, but not all of the enemy, while some of your other ships play a delaying action trying to keep a smaller portion busy. And then once your main fleet wins, then that swings into the other battle. And of course, technology greatly changes how much of this is doable in terms of how the winds are, the geography of the engagement. But there's a lot of interesting stuff you can discuss here. And then, of course, the mathematical question becomes, how do you determine how to split your forces and how to split the enemy forces? I'm doing two things here, two groups of two, because that's simple. Maybe you want to do three groups of three. How would you do it? How many do you put in each one? And again, keep things simple for the initial one. Has anybody ever played baseball or football, any sport like that, and caught a ball? Okay, and I assume everybody has a piece of paper with them so that they can do the calculus beforehand and figure out no. So we don't do calculus in real time in situations like this. You have a nice rough intuition after years of experience of where to go. And so it's interesting to compare, because Nelson was not solving differential equations, to compare his intuition of how should he split his forces by just experience versus what the mathematics says. And that becomes an interesting problem to look at to see, what would you do versus what was done. And so, here's a preliminary plan of Nelson of splitting into three groups of 16, 16. I don't have my ice glasses on. I think that's an 8 against what he thought the French forces were. And so there's what's called from the Lanchester model, the square rule, that basically the strength of your force, if we assume the ships are equally strong, is proportional to the square of the number that you have. And I'll roughly show where that comes from some of the differential arguments in a few minutes. And so if you look at the combined fleet, which had 46 ships, to the British fleet, which only had 40, you would see that the balance in favor of the Franco-Spanish Armada is about 516, which is a sizable amount relative to what the British have of 1,600. Hopefully the recording is going on, and if anybody's interested, I'm of course happy to chat further, but the slides and the video should be up later today. Okay, so that's if they just fought straight on. What if they were able to split? And so here, if they were able to split to 32 and 8 for the British against 23 and 23, all of a sudden the British have a slight advantage. And again, there's then some assumptions about how long would each battle take. Can the 8 British ships that are now facing the combined 23 Franco-Spanish ships, can they hold out long enough for the main British fleet to win and then swing back? And so it becomes an interesting question when you're looking at these equations. Roughly how long will it take for something to happen? Out of curiosity, how many people have seen the old Charlie Brown movies? Fewer hands than the Battle of Trafalgar. Interesting. Okay. So Charlie Brown never had much luck on his baseball teams. And so I love using this picture to try to highlight the issues when we do mathematical modeling. We want the model to capture the key features of the system, but we also want it to be mathematically tractable. And the more things we put in, the harder it's going to be. Now, with computers, this is not necessarily horrible. We can still run simulations. We can still numerically approximate things, so it's not as bad as when I was younger. But if you want to get a nice closed form solution where you can then see, well, what would happen if I change the parameters without having to run simulations again? It's nice if you're able to do this. And so in the last talk, we saw a wonderful progression from a very simple model to let's start adding more and more terms to it. You probably see this as well when you look at the predator-prey model, when you start putting in secondary terms there to describe how things are going to evolve. And so we want to have the simplest possible model that's capturing the key features that the students can work with. And so, similar to the last talk, let's assume that the British, we're no longer going to say British and Franco-Spanish because that could be offensive. So we will say red versus blue. And so red will have effective fighting value of N, blue will have effective fighting value of M. The simplest case, of course, is going to be when N equals M, but we can consider more general situations. And we'll assume that the rate of change of the blue ship is going to decrease based on the number of red ships. It makes sense. The more red ships you have, the fewer blue ships you should have a little bit later. So this is a very reasonable model for students to come up with. you can discuss just how reasonable is this going to be. It doesn't really matter if you have a large number of ships, if they're all in a straight line and only the first ship is facing the enemy, it doesn't matter how many ships I have behind. At any moment in time, only one ship is firing. This is why you often want to talk about like crossing the T, where you have the enemy ships coming in a straight line. You have your ships, there's a horizontal line here, so all the guns can come to bear on the first ship coming in. So just how effective you are is going to depend on the geography of the situation. But for simplicity, let's not worry about something like that right now. And let's just say initially, the decrease in blue is going to be proportional to the number of reds and vice versa. So we can talk a lot about why is this a reasonable model. And again, most of my students are not going to be commanding fleets in major naval engagements. I want them to get a sense of how do you do mathematical modeling? How do you start off with something simple and add more and more terms, and to be aware of the limitations of what they're trying to do. And then I always like to ask, special cases. As I mentioned before, the case when n equals m is the simplest and most natural one to start with. Okay, so if we want to solve this equation, this was mentioned a little bit briefly the last time. If we just take another set of derivatives. Okay, yeah, I said it's getting really bad. Oh, it's much easier. Okay, I couldn't tell if there were two derivatives here. Yes. So b double prime would be negative n prime, which is n times m times b of t. So this is a nice differential equation, which students should have seen before in Calc 1, Calc 2, and have some familiarity with solving something like that. We can explicitly write down the solution, and we can get a sense of what's going to happen in the limit. And from this, you can get the square law just about how strong things are. And so I don't want to say too much about that right now. I want to talk more the high level of trying to use this in a class to excite students about what mathematics can do. And so we can start plotting lots of different things. And if you want to plot things, you can put in specific values of what your initial concentration of forces are. Mathematica has a beautiful command called manipulate, where you can actually let the initial concentrations be variables, and you can have a little video, and you can see how things change, and you can plot, and you can actually physically see in terms of the square laws and just how effective everything is. Lots of different things you can do in terms of showing the strength and what happens. And you're going through and you're solving the differential equations. Again, all of these stuff, it's now extremely easy for the computers to do. And it becomes an interesting question in the 21st century. Which skills do I want my students to actually have? I want them to have enough so that they know if a solution looks reasonable. And it's so easy to have a typo or whatnot and have the computer generate something that's gibberish. I want my students to be able to look at extreme cases and get a sense of what should be happening. What should happen as we have overwhelmingly superiority for blue over red? What should the answer look like? Also, you're trying to figure out what answers are reasonable. So if, as I said, I'm a baseball player. If a baseball player hits the ball, we'll assume no air resistance. You have a nice parabola, and you can ask, when does the ball hit the ground? And you're familiar with how you calculate this. It's a nice example. There's actually two places where the ball hits the ground when you do the calculation. The other one is, well, the ball started at a certain height with a certain speed. You can run time backwards, and that will give you another solution. Now we ignore that because that's from before the contact happened, but there is two solutions in that. If you continue to use the differential equations beyond a certain point, let's say there's more blue ships than red ships. Let's say the blue ships have at least equal fighting ability. They will triumph over the red ships. And then all of a sudden, you now have a negative number of red ships, which means if you keep going forward, blue ships start to emerge from the ether. And so you need to be very careful whenever you're doing something like this, that where do I expect these equations to be valid? And you can't push them beyond a critical time. So how do you find where that critical time is, and you should stop things? Right? You can plot how many blue ships survive, versus going to battle against one red unit. You can ask, is this reasonable? Very natural question to ask as well. As I get more and more blue ships, and I'm only fighting one red ship, how many blue ships should be left at the end? So if I have larger and larger forces of blue fighting one red ship, how many of the blue ships should survive? All of it, or almost all of it, exactly. And so the difference should be becoming smaller and smaller and smaller. So just getting some rough sense of what you're trying to see. All right, so what about this one? Do you think this is a reasonable plot? And I do apologize for having an interactive talk at 8:30 in the morning, but for those of you who are hopefully coming from the East Coast, this is really like 11 o'clock, so this is fair. All right, so the vertical axis is the size of the blue force, the horizontal is the time to wipe out one red unit. Do you buy this? Does this seem reasonable? So what kind of test can you do to test to see if this is reasonable? Yeah, extremes. So the vertical axis is the size of the blue force, and the horizontal is the time that it takes to wipe out. So which extreme would you like to do for the size of the blue force? And I'm sorry? Really big. So if the blue force is really big, how long should it take to wipe out the red force? Yeah. And we can see right now, is it becoming asymptotic here at 2.5? I don't know. I'm a little worried about that. But I don't have quite enough information. And this is what's going to happen in life. You're not going to have all the information you want. This is the information I have. I'm a little concerned about how steep it's going over there, but maybe it's okay. So that's one direction, is if I have a huge amount of blue ships. What's the other direction? So one possibility was I have a large number of blue forces. What's the other one? Very low. And so, in fact, if I have the same number of blue as red, then blue should not be wiping out red. And in fact, if blue is less than red, it clearly should not be wiping out red. Well, if you look over here, if the vertical axis is the size of the blue force, then if you go down a little bit to below 1, I shouldn't be getting a finite answer for how long it takes to the red. There's something wrong with this plot. And what's wrong with this plot is the caption. And I do this because I've lost track of how many times I get images from students with no labels of axes and things are just wrong. And so the correct labeling is the vertical axis is the time it takes to wipe out one red unit, and the horizontal axis is the size of the blue force. So as the size of the blue force gets larger, the time it takes gets smaller. This is reasonable. I'm a huge XKCD fan. This is one of my favorites. I think we should, two people talking, I think we should break up. I think we should give it another shot and give a plot of their relationship. Maybe you're right. I knew the data would convince you. No, I think I can do better than someone who doesn't label their axes. And so just trying to really drive home to the students how important it is. The picture is worth 1,000 words. That when you are presenting information visually, you have to make sure things are clearly labeled. Be skeptical about some of the stuff you're seeing. There's another XKCD, which I'm not going to really go through now. This will just give you some incentive to go and look at the slides online. So there's a lot of opportunities for doing additional stuff. So, we did the special case of n equals m. You can give to the students, the problem of, how would you try to optimize, the split of the forces. This is doing the split into 2 and coming up with some, simple equations to look at. But you could, as was mentioned in the last talk, I think it was one of the questions, could you do this with 3? Absolutely. And try to figure out how would you do it like that. Then, the next natural question would be, what other features could you put into the model to make it more realistic? Where could you try to find similar equations that govern other things in the real world? This is one of the things I really like about the book, the 6 pillars of business calculus, where they took the SIR equations, and this is a book that came out during the pandemic. And as I'm reading this in chapter 1, I'm expecting, okay, this is another one on the modeling of epidemics. No, it's modeling the penetration of a new product in a market. Just for closure, to talk about the end of the battle, while Nelson died, the British were triumphant. They beat the combined French and Spanish ships. The Franco-Spanish fleet lost 22 ships without a single British vessel being lost. So the numbers are incredible. The British were 0 for 27. The Franco-Spanish Armada lost 22 of 33. But it's actually even worse than this, because the British actually ended the battle with more ships than they started. So they did not have naval crews building ships in the middle of battle. Back then, you could actually capture the enemy ships and bring them onto your side. And so it was an absolutely overwhelming battle. And for the students, it's interesting for them to see, some of the applications of mathematics to real world problems that have historical stuff, and then for them to actually go to their history class. And they've actually talked about this in your class on European history of trying to understand how you would do stuff like this. Right. Other things you can try to do for fun is, this was all completely deterministic. well, you could try to make things, stochastic, put in some randomness in terms of what's going on, run some simulations, try to get a sense of, what might happen. And this is a nice opportunity to talk about stochastic differential equations, a lot of opportunities to go from here to finance. I teach at a small liberal arts college. As I said, there's a lot of people who are interested in finance, and we don't have that many contact points of that in the curriculum. So thank you.
Are there any questions you'd like to ask James? You want to ask us?
Yeah, turn about spear game.
Have you done any stochastic or random stuff where students don't like?
I haven't done stochastic stuff for this. I've done stochastic stuff for other problems. And again, one of the greatest issues is what computer background do students have? And students are often very good at data scraping and whatnot, but not as versed in programming.
Another question. Do students have a sense of why this battle, for example, if you dwell on it, was so important, like for the control of the seas in terms of the period?
So some of them have a historical knowledge of why this battle was so important, and the fact that Britain was an island nation, that for them a navy was not a luxury, and a lot of World War I, World War II, the concern of the British. One of my favorite stories is when I think Churchill was, Lord of the Admiralty or whatever his position was. He was in negotiations with Parliament before World War I over how many dreadnoughts should the British build, and they were quite concerned about the rise of the German Navy. And they were trying to argue to them, you don't need a navy other than to go after us. And so Parliament thought that 4 dreadnoughts would be enough. Churchill thought 6. So of course, when you have a disagreement like this, you get together and you negotiate. Anybody want to guess on the number they settled on? Parliament 4, Churchill 6. 8 is, who said 8? Do you actually know the answer? 8 is correct. 8 is, you are the first person to ever get this right. They were negotiating between 4 and 6, and the more they talked, the more they realized, 6 is not going to be enough. We need to do 8. And so there's, so many wonderful opportunities, and I find students love it when they see that their courses connect across disciplines. When I can use material from one to have a more informed conversation with the other. And so going back to the question on Trafalgar, just pointing out how important it was for Britain to have control of the sea, to be able to move troops around, not to be in fear of an invasion because they don't have the same land forces.
Yes.
Yep. Yes. Right. We actually don't have that many engineers. We have a couple of students who take engineering classes at other schools and over like more than a 4-year program, sometimes with economics. And so there's a lot of stuff you can do in terms of that. Of course, obviously physics. So I was a double geek in math and physics, and I love doing examples from physics. Chemistry a little bit with for instance, like reaction equations. It becomes some nice applications for something like that. And then I love to do mathematics of sports. And so I haven't done too much with differential equations with that, but I've used that for a lot of other examples. And that's, in fact, your question is actually why I'm here, is I'm trying to look for more examples that I can use to try to excite students with extremely diverse backgrounds. And so most people have some sense of history, and even if they don't have a full sense of history, they can appreciate just how important something like this is. After the pandemic, it's almost mandatory to talk about virus propagation models. Everybody has been affected by the consequences of these models. And as was, I think, mentioned in the time after the first talk, we have to be very careful as professors these days in terms of what do we say. And so talking about the pandemic response is a incredibly challenging situation. But these math equations have been applied. And because they've been applied, you can have questions about what is the responsibility of a mathematician for how the equations are going to be used. As a voter, what is our responsibility for understanding consequences of models as we are making decisions on what to do? So there's a lot of wonderful conversations you can do.